AP Computer Science, AP Calculus BC, Unit 6, Day 1. So this is the beginning of our second semester. And this unit, we're going to do a little review and some new stuff. We're going to be focusing on differential equations. Differential equations are essentially derivatives, equations with derivatives. And so we're going to be sketching slope fields, but also one of the big things is solving differential equations, which we did in Calc, AB. We do have some new integration techniques that can help us solve some differential equations we couldn't before. This is the assignment. I thought we could just use this as some quick notes. So a differential equation just means that it has a derivative in it. And these, what we're going to do is we're going to sketch slope fields for these. So slope fields are just little tangent lines, little line segments that have the slope of the derivative, and it creates sort of a vague picture of the family of functions that could be the solution to this. Usually there's infinite possibilities because of the whole plus c issue. So, we could just plug 0, 0 in, and the derivative dy dx would be 1. So here we draw a little line with a slope of 1. You use the dots up 1 over 1 to kind of help you sketch it and write. We could do 1 at 1, 1. And dy dx would equal 2. So that'd be right here, slope of 2 would be up 2 over 1. So I can use these nearby to get the slope right. Now, this would take forever if we were just to plug each individual one in. So what I usually do is I look for where the slope's equal to 0. So, okay, well, where is it equal to 0? And that would be when x equals -1. So along x equals -1, we have a bunch of 0 slopes. 0, 0, 0, 0. I also look for like undefined slopes, which would be like infinitely steep because of division by 0. And there are none here, but those are usually like a nice thing to identify right away. There's usually some kind of symmetry in these graphs. And so probably along this line, there might be the left side and the right side might look the same. And you could confirm it. You could be like, okay, well, in fact, you might notice that really this graph only depends on x, which means that whatever x is, that whole vertical line is going to have the same slope. So if you plug in 0, 1, it has a slope of 1. You plug in 0, 2, it has a slope of 1 because x equals 0 for all of those. And the y doesn't impact it on this one. But future ones are going to have y's in them. Now, I bet these might be -1. If you plug -2, 0 in, you get -1. -2, 1, you get -1. So the thing you should realize on this one is that whatever the x is, it's going to be the same for that whole vertical line. So this was 2. So these are all going to be up 2 over 1, up 2 over 1, up 2 over 1. And I bet these are going to be -2. You can just try one, like -3, yep, -2, -2, -2. So we're looking for patterns to speed this up. If you plug 2 in, you get a slope of 3, which is up 1, 2, 3 over 1. So you could get, and try and draw all the other ones so that they're parallel, same slope. 3 would be a slope of 4 up from here all the way there. That'd be a slope of 4. So it should look steeper than the other ones. It's going to be kind of hard to tell. The key thing is they better be positive and negative. Or it's supposed to be positive and negative. The 0, 1 should stand out. So that's how we do these. The next one depends on y, right? The next one depends on x and y. So look for patterns. Now, the other thing I want you to do on these that isn't explicitly said in the directions, but I'm asking you to do it, is I want you to solve the differential equation. So solving the differential equation involves separating the variables. This one's pretty easy because the x is already on the other side. To undo the derivative, you usually want to separate the variables, right? Get the x's with the dx, the y's with the dy. Integrate both sides. This one's going to be y equals x squared over 2 plus x plus c. So this is they call it general solution. If we had an initial condition, then we could plug in to get the c value. But this is a parabola, and on here you should see parabolas. In fact, it's a bunch of parabolas, higher and lower than each other. So this should make sense with that. It's kind of a good check. Now, what if I told you to sketch the particular solution? So particular or specific is one of these instead of the whole family. And I would give you some initial condition, like say -2, -1. So what you would do is you would identify that point. So this is just an extra thing, but let's just do this as notes because you're going to have to do this. And then you try and follow the slope field. And it's not going to necessarily go through other obvious points. In our slope field, we could make more higher density we don't have to just do the nice points. We could have done the half points, but this would be the particular solution. And you know it should be 0 right around here, right? It shouldn't cross slope lines though. It should follow the flow. It should never cross these, otherwise it's wrong. So that's a particular solution. This is the general solution. So like later on problem 7, it says differential equation, sketch the slope field. They ask kind of a unique kind of question. C says find the particular solution, which means that you're going to find the C value when you're done. The other thing that you got to watch out for on these is that you're required to give the domain of the solution to the differential equation. Okay, so one, you got to remember to give the domain. 2, the domain relies on the answer, like regular domain issues, but it also relies on the original derivative having to be defined, and it's only a single open interval. And that also applies to sketches of the graphs. If there's any point where the function's undefined, you have to break it up there. If there's any point where the derivative is undefined, you have to break it up there. And you can only give a single chunk of it, whereas we usually describe the domain of a function as all the places where you get valid answers. The solution in the differential equation is different. So try this assignment. There's sort of an, I guess, a little interesting different question on the back, sort of applying it to some kind of more real world type of problem. And I will make a video later talking about how to do each of these problems. So try these on your own. Please give me the solution, the general solution to all these. Now, I'll give you one hint right here. On problem 3, we can't find the solution. Okay, you can do the slope field. It has a solution. Since we can't separate the variables, it's impossible to separate the variables on this problem. You can't get x's and y's completely separate from the dy. Like on this one, by the way, separating the variables, you want to bring the y over here with the dy and the dx over here. I'd leave the 2 on the left-hand side. So this is the way I'd write it. I'd write, okay, this would be dy over y equals 2 dx. So that's separating the variables. And then I'd integrate both sides. And you get natural log the absolute value of y equals 2x plus c. Now you got to get y by itself. You got to solve for y. So anyways, the sketch that you get, do the slope field first, and then the solution you get should make you think of the type of function that you get. So, all right, try them yourself. A little review today. Nothing new from Calc AB.